Now we'll ask Adam, Tom, Chris, and Roger to come back up to the front for our panel discussion. We're going to be aiming for a maximum livelihood discussion. This really should be a debate and dialogue. The speakers themselves have been thinking about a lot of the most pressing questions in advance of the panel. And there's also an opportunity to build not just from your questions in Slido, but your live questions as well. So each of you take a chair and you each will get your own personal microphone. And Roger, no avoiding the panel here.
I'm being penalized.
Sure, yeah. Great, okay, so the overall areas of questions are multifaceted. There are a lot of questions that will be deep dimensions of the risk and the complex relationship between cyclones and a change in climate and precipitation and drought. There also were a lot of questions that came up about the role of scientists in communicating that complexity or not just through assessment, but also in their public remarks, their interactions with decision makers and policymakers. As the final major area of questions that came up both in advance with our email discussion and also via Slido is how to think about responses unfolding in real time and how the nature of needs for science to inform that decision making and for science to study that process of decision making and response changes and looks different from some of the talks you heard today. So I think where I'd like to start is actually the question that Adam put out into our very first email, and then it was exactly where Tom started today. And that's this basic idea that if you're doing the science of cyclones, this is not like the science of how a change in climate affects global mean warming. It is invariably much more complex. And Tom, I thought it was really cool to see the way you adopted a type 1 error aversion pillar number 1, but then also not being limited by that. And that's really a place where assessment of complex challenges has fell flat in the past, and it was really cool to see this balance of evidence approach and being nuanced about that. But then there's also this question of, yeah, when policymakers say this is climate change, or Fridays for the Future, a young child saving the planet says this Hurricane Dorian is climate change. What is the role of science, and how have you personally grappled with the complexity of this issue and the real-time needs for information on it?
Gosh, that's an interesting question, because I think there sometimes I've noticed sort of a tendency to jump to a conclusion sometimes that, well, this was a climate change producing the hurricane, or it had no impact at all. So what we're trying to do is bring a rational approach to the whole problem, to try to differentiate between these things which we're very confident about, like global mean temperature, versus things where the science is still somewhat unsettled. It probably came through with some of the talks today. And you saw some of the reasons why it's so unsettled, because there's some of these subtleties going on, like Adam brought up, where there are competing influences that are sort of hiding the effect of greenhouse warming on tropical cyclones. So it's a complex, the way we're diagnosing it is a very complex situation, and I'm most comfortable with something like global mean temperature, where you see in the data the actual effect emerging, and you see that models do a very good job of simulating that, and there are no convincing alternative explanations. So in that case, we can make very strong, confident statements, even using this type 1 approach. The reason we had to kind of go to this type 2 approach for tropical cyclones is because we felt that, we had some conversation with Adam about this, that we felt that if we were just using the type 1 approach to assessing the problem, that we were essentially saying nothing, but we felt that we could say something. And we were obligated to say something, if nothing else, for the risk assessment perspective. So the type 1 error approach, I think, is what scientists are comfortable with. Do we see it in the data or not? Is it present? That's sort of a shorthand way of looking at it. But there are cases where we have reasonable expectation through theory or modeling that there is a human influence, but we We can't yet demonstrate it. We can't yet say, oh, here's the smoking gun in the observed data. So what do we do in those cases? And so, and a good example of those are these attribution without detection type studies for extreme events. How do we treat those? So if you turn the question around and you say, let's instead of wearing our scientific hat for the type 1 error avoidance, let's put on this other hat, the type 2 error avoidance, for the benefit of people that, for purposes of risk assessment or other means, want to know something even if it doesn't rise to the 0.05 significance level or something that we're looking for. So, and we applied this different filter, and then we had quite a few statements to make about possible detectable human influence on tropical cyclones. But one has to recognize that those statements, because we haven't applied as strong a rigid a filter to them, are more likely to be overturned or modified in some way. Maybe they're too weak, maybe they're too strong, but more likely to be quite a bit modified as the science evolves further. So you're getting kind of a look at the science at the bleeding edge, I think, through this type 2 error avoidance. Hopefully that's not going to be too confusing to people. We try to explain what it was we were doing and why we were doing it. And with some caveats, there are caveats in the paper. So now whether IPCC adopts this kind of framework, I don't know. I'm not really involved in that report. We have some discussion, informal discussion with authors. But it's very different from the typical way IPCC does things. I think they tend to be in the type 1 error avoidance approach. But we're just dealing with a problem, tropical cyclones and climate change, and I think there are other problems sort of in the same general class where there's a lot of uncertainty about the climate change effect, where this alternative framing of the state of science and our assessment of it, we think may provide some utility to our audience. I think it's a question of what is the audience looking for? Are they looking for a really solid conclusion? Because there are different ways we can come to this solid conclusion. We can look for agreement between different modeling studies. We can look for the presence of the trend actually in the data. We can look for strong mechanistic or theoretical understanding of what's going on. These are the types of things which lead to higher confidence. But in many cases, we don't have those things for all these. So when you don't have them, then naturally your confidence is going to be somewhat lower. But still, we think that it's worth reporting these things from a type 2 error perspective, just more as in the spirit of communicating something about the science, where it's somewhat preliminary in nature.
And just to run with your theme of the IPCC, I can say that your colleague in Princeton, New Jersey, Michael Oppenheimer, injected a very similar approach into the latest sea level rise assessment to really say, we can give you the best guess, but that's not what a risk-attuned decision maker might need. And Adam, since you threw out this question of what is an ethical, responsible scientific approach when the science is complex, do you want to take it on as well?
Yeah, I'll try to give a little context to what Tom said, which I agree with everything he said. So, the traditional way we're taught as scientists is we just do the science and we put it out there and, in scientific papers, and then how it gets used is not our job. And there's a lot of scientists who do more than that, but that's sort of the way we're trained. And I think for those of us who work in areas like climate, which are so both important and very contentious and where the work has a lot of import, many of us have come to realize, both individually and sometimes even at the institutional level in some cases, that we should go beyond that. We should think about how the information is going to land when we put it out there and be a part of that. In other words, not just lead it to somebody else, and that includes thinking about the political ramifications, because the scientists and the historians and philosophers of science will tell you that there's no such thing as science not being political. It's always living in a context, and if you pretend that's not there, that just means you're not in control of it. Somebody else, you're accepting unconsciously somebody else's context, and maybe you should think about how you want it to be used. So how this comes into event, I think I can tie in everybody's talk here. So how that comes into, that's a general statement, but how it comes into the conversation here, so Tom's talking about the type 1 and type 2, and so event attribution, so the traditional detection attribution is you detect a trend, you say something's changed, and then separately attribution is you say, well, this is what the cause is. And the traditional way of doing trends is, it's a so-called frequentist statistical approach where you try to see, is this, can you reject at 95% the null hypothesis that there has been no change? And that's a historical accident. That's a very conservative standard. If you know that the climate has changed, then, why 95%? Why is the null hypothesis no change? Why do it that way? The Bayesians do it totally differently. So event attribution, which is a relatively new science, I actually think, I'll go out on a limb and say, I think event attribution is when we used to say we can't attribute any one, it grows out of traditional detection attribution. It was invented by people who had come from that, but they took it a step further and said, instead of when there's an extreme event like a hurricane saying, well, you can't attribute any one event to climate change, they said, well, maybe you can in some partial way. You can never say it was caused by climate change because there's always been hurricanes, but you can say maybe the odds have changed. And I will go out on a limb and say that science was invented to influence the political conversation. It was invented because when there's an extreme event, the media is focused on the atmosphere, the climate system, in a way that isn't any other time. And some scientists realize that's a time to get people's attention. So when they call us and ask us, was this climate change, we should have a better answer. We actually believe that there's some connection, and so we should try to make that connection more scientific. So that's where event attribution comes from, I think about 10, 15 years ago. And then what happened next was you could do that for some events like heat waves, as Tom said, because they're related to temperature. You can make a sort of statement that's compelling. But when it comes to a hurricane, the science is uncertain enough that you couldn't make a strong statement in the traditional way where you say, this hurricane was much more likely because of climate change. We can't say that. So then what happened in more recent years is people developed the attribution that the method that Chris talked about, which is, and that she used in her research, which is where you don't ask that question. Because that, to say the hurricane was more likely requires you to know about hurricane frequency, which as I talked about, we don't really know anything about that. But we do know that the hurricanes occur in a different environment. So we can sort of say they're getting stronger. So you can say, well, if this same hurricane had happened in the past, with everything else being sort of similar to the other conditions being sort of similar, but the climate being different, it's probably a little stronger now, and she can do the science to tell you how much stronger it could be, and so on. So that was developed because the traditional attribution approach, which is self-developed, I think, to influence the media, which by the way, I would say is fine. I think that's fine, as long as it's done responsibly. That approach left people sort of saying nothing with some kinds of extreme events, because the science was too uncertain. And yet you scientists knew, as Tom said, they could say something, it just what they could say didn't fit in the traditional attribution framework, so that was changed. So that's an example of people thinking about how what they're going to say is going to land in the outside world, and it actually affects the science. Now, there are a lot of other ways scientists can be engaged. You can have your science not change. You can, work with, your local governments to help them write adaptation plans. You can do all kinds of things. And we all have our own responses, and some people just want to keep their heads down and do the work. But I guess what I would say more broadly is I'm having a bit of a, I'm thinking a lot about this in my own life now that I've got to be, a person whose career is fairly stable, and I think that I'm old, But it's fairly, it's easier for people whose careers are established to think about these kind of things than it is for young people, because I think, or junior scientists, I should say. It's about academic age, not chronologic age, but the incentives of scientific careers still don't favor doing anything but the scientific work and publishing it in the journals and speaking at conferences, and getting grants funded. But I think that for those of us who believe that our work is important for how it affect society, it behooves us not to be naive about that and not to imagine that just doing the science is going to lead to some good outcome, and that we should be more conscious and deliberate about how we think that might happen.
Great. Okay, I suggest from here that we flip to Slido. You can see some of the top voted questions up here. But instead of just reading them out one by one, I'm going to try to do a little bit of an integration across one of the themes that has come up across a number of them, which is precipitation. And these bundled questions, first of all, Chris, you described in some ways how to think about the different ways that precipitation is changing within a storm versus outside a storm. What is that linkage like? Tom, there have been some questions as to whether your trend detection around mean precipitation, where globally you're seeing more increases in mean precipitation than decreases, does that challenge the traditional simplistic truism that wet places get wetter, dry places get drier? Is it more that a lot of places are getting wetter? And finally, the direct question we've got here, attribution detection in the space of extreme precipitation, heavy rainfall versus mean, same, different, why, and how. So feel free to run with the theme of precipitation in any way you'd like.
Yes, well, I think that this notion of wet get wetter, dry get drier is not quite adequate to describe what's going on. I think it's not really describing the data. But what we're doing, and with this study that I did, it was a detection attribution study, but it was also a consistency study. So we were asking the question, are the observed trends we're seeing in something, in this case it was regional precipitation trends, are those consistent or not with historical CMIP runs forced with our best guess about historical forcing? So if they're not, then we have a problem. But a problem is also an opportunity to learn something. So when we have this sort of mismatch between what's observed and what we model, we have sort of four candidates for why that's the case. It could be that our models are wrong, they have the wrong sort of sensitivity to forcing. It could be that our forcings are not well constrained, so we don't really exactly know what the historical forcings were. It could be that we are underestimating the internal variability of the climate system, and really if we had the real right amount of internal variability, then we'd be consistent. There'd be a consistency between model and observations. And the fourth thing, it could be problems with the observations themselves. So we always have these four candidates. But I think it's an important exercise in science, in climate science, to confront the models with observations, find these cases like I'm showing where there are issues, and then try to learn from it. So what's coming out of our study is that there's a lot more wetting, this is for mean precipitation, over continents, a lot more wetting going on in the observations than in models. So models do a pretty good job of producing the global mean temperature evolution, but why should we expect they're going to be perfect for mean precipitation and its regional distribution? That's asking a lot of models. And so we're just saying that the early indications are, hey, if you're in the upper Midwest and New England states and higher latitudes, things are changing, if anything, more strongly than what models are suggesting, at least over the historical period. So it's a heads up that maybe you should be prepared, at least for the possibility, that the future projections will also be stronger to the wet side. So now this is about mean precipitation. Now IPCC is also assessed precipitation extremes, and IPCC concluded that there is at least medium confidence that there's a detectable anthropogenic influence on extreme precipitation, at least over land regions where there's adequate data. So there is, IPCC's already made statements about extreme precipitation, and it's tending to increase, and that increase is very strong, by the way, in the US for some reason. The Northeast US is kind of a place where that's really prevalent, this increase of extreme precipitation. I think both are changing. Both are going to the increased side. Which one is the stronger signal? I'm not quite sure. I wouldn't say about that. But it is something we have to keep in mind. Because precipitation, I think, has a lot to do with drought risk and also flood risk. It's an oversimplification. There are other things involved, of course, in these things. But it's one of the major players in drought and flood risk. So it's just a wake-up call that, hey, there may be something not quite right in the models. So let's keep an eye on that. But in any case, both extreme precipitation and mean precipitation are showing, tending to show a lot of increases in the data. So now there are regions of decreasing mean precipitation, and in the Caribbean, as Roger pointed out, there's some areas that are drying. The Mediterranean region is kind of a region with a lot of drying going on, and parts of tropical Africa, century scale drying. So there are, and the southwest coast of Australia, the drying trend is so strong that they've actually had to build desalination plants and give up on the reservoirs there. So there are things, if you look at that map of what's going on, there are little stories all over the place that you could kind of go into in detail. So there are changes going on, both positive and both drying and wetting going on around the planet over the last century or so. And we're just trying to sort this out a little bit and see how models are doing with capturing these different changes. So, but it is, I think precipitation in general is an important part of the climate change story, and that people are going to have to deal with its impacts.
And Chris, on the theme of kind of dissecting storms and understanding what's going on with precipitation inside and around a storm and changing climate, do you want to add anything on that?
Yeah, sure. So I think I had seen a question pop up that was asking about the precipitation change, the structure, the spatial structure and the precipitation change from the simulations that I had performed. And the two that I showed where there were maximum increases towards the center of the tropical cyclone and drying in the outer parts of the TC, those were actually in the minority of the 15 cases that I had looked at. And so, one of the big questions that's been floating around in my mind is, what's causing that, and what was it in particular about those hurricane events that led to that response? And so a lot of times when people ask me about, precipitation change, I think the Clausius-Clapeyron has been sort of getting out more into people's sort of the knowledge of the public. And so people kind of start off with that as, I guess, sort of the starting point. And I guess, trying to better understand, of course, that's a kind of simple thermodynamic estimate. And so trying to figure out, I would say the real uncertainty is not whether precipitation in these systems is going to increase, but by how much, and if it exceeds the Clausius-Clapeyron estimate, by how much can we expect that? And I would say right now, there's a lot of uncertainty in that aspect as well.
Roger, I saw you grab your microphone. Do you want to weigh in on this one?
No, this is fine.
I've got another question for you. Okay, we'll go with the next cluster coming out from Slido, and then we'll open the floor for any questions you've got, and we'll make sure we kind of get to coffee break on time. So a cluster of questions is around time frame. So the first one is, has the option of managed retreat been considered yet? We're going to skip that one because it will come back tomorrow, and I have some opinions on it. But the other, more directly related to this set of presentations, question around time frame is really how some of these dimensions of time play out along the challenges of detection and or attribution. So, for example, when you've got modes of variability at different time frames, to what degree does that challenge your ability to say whether there's an anthropogenic signal? Adam, building from your GHG versus aerosols, has the greenhouse gas forcer taken over, outpowered aerosols yet? When might we know? And Roger, I'll throw this question of time frame to the decision-making realm as well, because I feel like it's deeply relevant there. If we're twiddling our thumbs until we know for sure exactly how cyclones are changing in a changing climate, we may have some issues. So yeah, the challenge of it will take a long time to know the answers to many of these questions, some of them in the space of multiple drivers interacting, some of them in the space of is this variability or climate change, and how do you grapple with where science should be tackling these themes next.
You really want me to do it?
Yeah, well, no, the piece I thought you were asking was when are GHGs taking over? Was that your first spiel?
Take the broader thing.
Oh, sure.
Yeah, we haven't heard you talk yet, Roger. So
Oh, well,
go
you'll
for it.
regret that. So, as we think through the time frame issue, because it's linked to the question I was trying to make Adam answer instead, you know, on when we see a signal. So what have we learned about adaptation? We learned that people sometimes need to see something in order to respond. Yet our data or assimilation is so sparse that it actually, we've shown that sparse data systems actually delay adaptation choices because it takes too long to aggregate over the signal. So that's a big issue. I used to be on the steering committee of the Global Climate Observing System. This was one of the big issues with adaptation. But this is also why we're raising the question that the predict then act sort of framing doesn't apply when complex systems and indeterminacy is ruling the day. That doesn't mean you don't predict. You do, for the things we can say something about. But you do it in the way Tom was describing, as a type 2 sort of error that helps us understand what choice to make, as opposed to asking, how precise do we need to be before we act? How precise we need to be before we act is actually a failed notion of how decisions actually take place. Works really well in decision analysis and Bayesian approaches, but it's actually not how humans make decisions. Our links are much more related to cognitive issues, who is already doing certain actions, what information are they using and how, and did it help them out? And so getting ahead of the game actually has to show what we call the triple dividend. That when you act up front, you're not only avoiding a loss, but you're creating co-benefits in other areas that you can benefit from. And that was related to the question on being able to show benefits not just in the realm in which you're adapting. In other words, if you have a wetland, yes, it helps with wave energy, but it also helps with water supply, fisheries, and everything else. There's that part of it, but then there's also the issue, and we heard some really good presentations, of why the idea of resilience involves networks. The idea, our missing piece, well, as somebody says, you know, when you're here and you say something is missing, it is not missing, you just said it, right? The issue is that if you have adaptation buffers, you're actually buying off future risk. Yet our actions are not commensurate with recognizing that adaptation buffers are needed. We use up wetlands, so our notion is to show the value of those things in the upfront. The idea of waiting to be specific to a particular prediction is allowing other confounding factors to take over. And so what we want to be able to do is show the near-term benefit of making broader decisions such as these. And there are good examples of doing that in insurance where you do, and I think Carolyn will talk about that, where you have, you know, public-private partnerships to do that. But where we're not seeing enough of is the community acceptance of the needed adaptation options. And a big reason for that is that we're not showing that the benefits are broader than simply responding to an extreme event.
Great, and Adam, do you want to run with the theme of GHGs versus aerosols? Have GHGs overtaken aerosols already in driving cyclone intensity?
Yeah, I don't know what the definition of overtake is. I mean, there are two things that are competing, and if you look at the global time series and potential intensity for whatever that's worth in the models, whatever they're worth, it suggests that the greenhouse gases are already larger. The increase is already larger, and there are quite a few studies that have already seen in observations increases in hurricane intensity, which suggests that that's true, although there are lots of arguments still over the data in those studies and how they're analyzed, but more of them are suggesting it every year. It's also probably regionally variable because although the greenhouse gases are global, the aerosol impacts the aerosols themselves are much more local because they don't last that long in the atmosphere, so they're emitted someplace. They blow downstream a little while, and then they rain out. So the Atlantic saw big aerosol impacts in the 70s and 80s when we were emitting a lot of sulfate, and then that got cleaned up, so it's not as much now. Now India and China are emitting a lot more, so there's probably more impact over the Pacific, but that'll presumably eventually get cleaned up as well. So I think, I think the greenhouse gases are probably winning already, certainly in some places. The work I cited done by Amy's group here suggests that the last sort of cycle of Atlantic multi-decadal variability, in fact, is due to that. But there's only so much you can say about that because the actual data on the aerosols themselves don't go back very far. I mean, before the satellite era, we don't have much, and so it's not an uncontested area, but that's the way it looks.
And I know in the space of extreme heat attribution, this question of is it aerosols, GHGs, are they being treated separately has been an enduring issue over the last 5 years as that science has advanced. Do you see the cyclone questions being fundamentally different than the way this has unfolded for heat?
I'm not sure I know what you're referring to about
Gert Van Oldenburg's group, for example, in doing the real-time attribution is well, they can't attribute it, but it actually seems like it's because aerosols are damping out the effect that may actually be occurring.
Same situation. Yeah, same situation. I think it's a similar issue. Yeah.
Tom is jumping out of his chair.
Yes, so in the recent assessment that we did, the panel as a whole was not willing to conclude that the increase in Atlantic hurricane activity since the 1970s was due to reduced aerosol forcing. IPCC, the last IPCC assessment did conclude that with that there was an aerosol contribution with medium confidence. Our panel actually made no statement about it. And this was like 11 authors, and this was one case where I think I was outvoted because I was willing to make some statement, but I think it's a really difficult and challenging problem here in the Atlantic Basin where you have this, everyone agrees at least that there's strong multi-decadal variability of things like wind shear and major hurricane counts and things like that. What we disagree on, what I think is still unresolved is what is the fraction of that variability that's being driven by aerosol forcing changes, and what fraction of it is just a natural sort of fluctuation associated with changes in ocean circulation currents. And we have, I know some at my own laboratory that feel very strongly that the majority of it is really internal climate variability associated with AMOC, Atlantic Meridional Overturning Circulation Variability. And there are others, I know Amy, Mark Kane, and others are very convinced that really it's aerosols are the dominant driver of that multi-decadal variability. And as Adam points out, there are big stakes here because if it was aerosols, then we don't expect another quiet period like the 70s and 80s, whereas if it's sort of natural fluctuations of the overturning circulation, then maybe we would expect to eventually go back into a quiet period. So I think I'm not convinced myself one way or the other too strongly. I think it's still an unsettled question. We can try to look for fingerprints in the data to try to distinguish between the natural internal variability hypothesis versus the aerosol forcing hypothesis. I think that's something where more work could be done perhaps in the science community. It's a fascinating question. I think it really has real implications for people living in places like Florida and in hurricane-prone regions of the Atlantic Basin. So I think we could stand to invest more scientific effort in trying to understand that. Or we can just let the climate system play out and see what happens. That's a default. But I think what I'm advocating is let's stay a little bit ahead of the ball game and try to use our science to try to make some kind of rational judgment about which of these two hypotheses is more likely to be the case.
you want to weigh in?
Yeah, thanks. This discussion, I think, really nicely highlights the importance of being able to understand comprehensively all of the different drivers of extreme events. And so, like I was mentioning in my talk, and like everyone's been saying, natural variability is also really important. And so, absolutely, climate change is important as well. But I think one of the big questions that I think about is sort of what we might expect going into the future in terms of how the interplay of natural variability and various anthropogenic forcings could play out in terms of what that means for extreme events. So, one example is, we tend to expect to have active Atlantic hurricane seasons when we have warm conditions in the Atlantic paired with La Nina conditions. And we don't know right now, as the climate changes, both in the atmosphere and the ocean, if we have those conditions that, in present day variability tend to lead to, say, very active hurricane seasons, could there be sort of compensating effects of future climate change, or, could they be additive? And so some of the worst case kind of Atlantic hurricane seasons that we see now may be exacerbated by climate change in the future. On the flip side, I think this touches on some things that Adam was mentioning in his talk. We, in the Atlantic, during El Nino events, that tends to suppress hurricane activity. But the mechanisms through which El Nino does that involve both dynamic and thermodynamic variables. And so, we may see some changes in one or the other, where essentially we have to start thinking about how thresholds and nonlinearities in the climate system can play out when we're combining natural variability, which is very large, and the increasing change from anthropogenic forcings. Great.
I just had a couple of really short comments. I agree with everything everybody said, but just a couple of things to add. One is that, Tom's, of course, right. He said it a little more strongly than I did, but we agree that this issue of the aerosol versus natural variability is not settled. But I think an interesting thing to keep in mind is that if you'd asked the question 10 or 15 years ago, when the Atlantic multidecadal variability had already been documented for a long time, everybody would have said it was the thermohaline circulation varying. The aerosol thing only emerged, mid-2000s to my knowledge as a hypothesis. So so if it's even has some chance of being right, that's a direction where we're sort of being surprised by an anthropogenic influence on climate emerging sooner than people sort of recognize it, and in a different way than people recognize it. The other thing to say is that the stakes are even higher than we're talking about here, because not only did that cool period in the 70s and 80s cause suppression of Atlantic hurricanes, it also caused a massive drought in the Sahel region of Africa that killed huge numbers of people. And so the answer has big implications for that too.
Great, thank you. We'll allow one last lightning round of questions from the floor. If you've got a question, put your hand up, and I'm thinking we could take a cluster of them, like 3 at a time. I know Ben definitely has a question, but if any other people also have a question, we'll take them all at once and then allow the panelists to give one last round of reflections.
So Roger, having spent my entire career on prediction, I'm not in the least bit threatened by your
Wasn't
comment.
meant to threaten.
No, not in the least bit. But I did want to ask you this. I'm very much intrigued by your comment that we really have to think about the other derived benefits. Right. And to me, that sounds like a really hard problem. I buy it. I totally accept it. But that sounds to me like a really challenging problem. Can you identify where we've succeeded in that? Sure. Are there good examples that we can, for this part of the storytelling?
Yeah, sure.
Hold on one second.
Yeah,
if there are any other questions, we're going to do a round. Okay, we'll go to Kenny.
Anyone else who isn't threatened?
Yeah. Yeah, Kenny, go for it.
Go for it right now. Back to the aerosols versus AMOC, of course, for marital stability on the aerosol side. But does it matter from a societal preparation and adaptation standpoint? Would it make a difference?
Right.
at all.
Good question.
Fabulous. We've got
That's a good
Ben
one.
feeling
It's
threatened or
similar.
not.
It's similar. It's not
Aerosols
threatened.
versus AMOC, and we'll take one last question, and then we'll go to the panelists for their last remarks.
This might be related to what Roger was saying. You know, listening, you know, if you are a decision maker listening to this, you know, changing explanations of science, it's very, you know, very confusing because they're trying to make decisions on resiliency planning for sometimes up to 50 years. So I was wondering if the scientists should take another approach saying, there are certain things that have deep uncertainty and we don't know, but use the dynamic adaptive pathway option that the Dutch are following, for example, because that will be less confusing to them.
Great. We'll take all three of those questions, and just you all can go in whatever order you would like.
I'll give it a shot.
Roger first.
Yeah. So yes, and the aerosol versus, well, I don't want to make a mockery of your statement. But anyway, the idea of attribution, I think it's still important to society, even in terms of how we respond. In fact, one of the questions I had for the entire group was whether or not we needed a national capability on basically attribution. The reason being that we do have to figure out you know, where the aerosols are coming from, what the inputs are, because that also implies a specific set of decisions, if that's the case. The trade-off on attribution, and it's common in a lot of settings to say, well, we don't need to know what the cause is, we just need to know how we're responding, is that then, for the pieces that we might be able to do something about, there is an intervention, whether it's carbon markets or something like that. So there's still a societal role for that type of decision making. And in fact, to go back to the type 1 and type 2 issue, the reason why IPCC focuses on the type 1 area is because the IPCC studies and results are not meant for application and decision making. They're meant for negotiation. They're meant for getting at what some of these inputs are and how we agree on them, as opposed to how society responds to those changing events. And this has always been a problem when we're in IPCC, saying, oh, this isn't local enough, it's not meant to be. It's meant to be for the point of negotiation. To get to the issue of you know, whether or not one is threatened by saying something about predictability, which I fully agree with you. The issue is we have a great deal of successes. I remember saying, I had one guy who was telling me, wow, I was on the bridge in Maryland, and you guys couldn't tell me if the hurricane was going to come up all the way to where I was parked. And I said, I mean, come on, guy, aren't you even surprised that you know a hurricane is coming? I said, it's not been so long ago that society did not know. He said, well, I never thought about it that way. All right? What I'm getting at is this. The notion of where we think about resilience, the longest term adaptation buffer we have in the United States system is the Conservation Reserve Program that was put in after the Dust Bowl. 2.5 million acres put aside for hay, water, and forage if we go into severe drought. It's been there since the Dust Bowl. It's an area, something that provides a buffer. Now, the reason for taking the trade-off with efficiency or risk versus resilience is we think we're efficient if we're using everything to the last drop. And that is, in fact, a recipe for failure in a changing and uncertain environment. Carl Walters, the person that crafted with Buzz Holling the phrase adaptive management, we did an assessment of 200 cases around the world in watersheds on where the science, the integrated science was used and applied, and the decision-making or deliberative component was also set up. We could only find 3 of them in the 200. But there's some clear lessons from those where basically the role of not just the public being engaged in leadership, but a strong link between research and management, where that was crafted, were where those 3 areas were successful. Now, we might think of things like the Pacific Northwest, where the first adaptive management program was set up. There's a reason why there's still salmon there in spite of all of the pressures that are going on. It has to do with the collaborative arrangement around adaptive management. So I want to be sure that getting back to Obi's point, is the idea of a dynamic adaptive structure is you use the predictions when they apply. Right? When we were doing the drought assessments on the 2012 drought, then we have a paper coming out actually in Nature on the S2S event in the upper Midwest. There's no getting away from the internal variability of the atmosphere, at least in the case of drought. You'll have some drivers, land surface, SSTs, other things that contribute 50 to 60% of the variance. And a lot of the other is internal variability. So we're not going to get exactly what Adam was saying when, for any event, is our GHGs, for want of a better word, trumping the others. My reason for saying this is not that you throw up your hands and say, oh, the future is uncertain, how do we act? You use the pieces of risk that apply to risk, and you use the pieces of resilience that say, you know what, we need buffers in the system, like the Conservation Reserve Program, like watersheds, that allow us to withstand an uncertain future. The question is who pays for those? And unless we can show the value of those types of buffers have near-term benefits and can be designed with near-term climate information and projections and observations, then we're not showing a pathway for putting those things into place. In addition to the avoided cost and the co-benefit, is the issue that when you avoid a cost, there is now some pocket of funds that you can actually invest in new ideas for adaptation, and that's what we're trying to work on. So there are some cases, there are some examples, but I do want to say that in no way was I suggesting that the predict then act was a failure. It works in specific situations. There are broader questions surrounding resilience to which it does not apply. Yeah, me too. I was trying to pretend to be serious there. You know, there's a difference between attribution and retribution.
Great. Any last reflections from Tom, Adam, or Chris?
Well, I think getting back to this question about whether it matters, AMOC versus aerosol forcing. So I guess the one point is that in neither case was, even with some of these studies like the Dunstone et al. Study pointing toward aerosols, they're not pointing toward greenhouse gases as producing a large increase in activity in the Atlantic basin. So they're more talking about the past and maybe the near-term variability. So, but I think getting back to something Adam was saying, we also have other effects of this multi-decadal variability, including the Sahel drought, which was a very devastating drought, multi-decadal scale event in Africa. And so I really think it behooves us to understand the causes of that, and whether there were human contributions to that is also maybe a question of environmental justice, perhaps, and but also just for the future of in thinking about resilience in that region of what type of future variability they could expect in terms of rainfall. So there's some really important, I think, impactful questions around this whole question of aerosols versus natural multi-decadal variability around the Atlantic basin and its sort of teleconnections into nearby regions, including Africa and Atlantic hurricanes and African drought.
I think it matters a lot because if the cold period in the Atlantic in the 70s and 80s was forced, then the implication is that the forcing is playing a larger role than we thought, and the natural variability a lesser one. And so while there still is natural variability, and we could still go back to to a lower activity, lower cyclone and Sahel dry period again for natural reasons, the probability of that seems lower if you think the last one was natural than if you think it's anthropogenic. So to the extent that so that makes it relevant to the present and the future. And of course, it depends on the certainty. I mean, you could also, to get back to the other issue of what you can predict and what you can't, of course you could say, well, we don't have high confidence in any of this, so maybe it doesn't matter and we should just take a risk-based approach and think anything's possible. I mean, there's a spectrum of, it depends what kind of decision you're making, but I think it's as consequential as almost any argument about specific events in the recent climate history.
Well, we can argue offline. I was really referring to adaptation, not mitigation, which
right.
you
That's what I
answered,
thought.
and specifically to Atlantic hurricanes. I didn't mean Sahel, et cetera.
Yeah.
So.
Great, and we'll give Chris one last opportunity for the last word if you would like, and then we're going to go to coffee.
I think since I have coffee, maybe y'all should
You're happy?
Yeah.
Good. Great. Let's
Can
give
I-
a big
can I
round
give you,
of.
before you end.
Hold on.
Yeah,
Roger's
there is
got a last
something I
point.
wanted to mention, right? For those of you engaged in this activity globally, there's a major event in 1984 led to Live Aid and Band Aid, right? That led to one of the worst droughts on record, East Africa. 400 to 600,000 people died. 2013 to 2016 was a worse drought than that in Ethiopia, and because of the cooperation of international scientists, observers, and food security people, it didn't turn out to be a famine. Right? We have cases in which we know and understand how to build networks, how to get information on the ground, how to work with people on livelihoods. We just have not scaled that up to where we think about it as an entire nation.
It's great, and we need to. Big round of applause to Chris, Adam, Roger, and Tom. Thank you all.